Hi everybody, Dr. White back again. This time with geometric series. They're special type infinite series that are pretty easy to analyze once you figured out how they work, and they occur in a lot of applications. So suppose you've got a series of this form. Sum n goes from 0 to infinity of c times r to the n, where c is not 0 and where r is not 0. Okay. Such a series is called a geometric series. If you wrote out the terms, c times r to the 0 would be just c times r to the 1, c times r squared, and so on. And you'll notice that each term is r times the previous term. Okay? That's always the sign of a geometric series. Each term is a fixed number times the previous term. So, examples, they're all over the place. The cake eating thing, that infinite series of how much of the cake you eventually eat if you just go on day after day after day is a geometric series, because you could write it like this. You see the term here, when you let n be 0, is 1/2 times 1/2 of the 0, which gives you your 1/2. If you let the n be 1 in that term, then you'll get 1/2 times 1/2 to the 1, which is 1/2 times 1/2, which is 1/4, and so on. So the c here is 1/2, and the r here is also 1/2. Okay. Now this infinite series could be written. This infinite series here could be written in alternate ways. You could write it as the sum from 1 to infinity of 1 over 2 to the n. In fact, I think that's the thing that would occur to most people first if they were asked to write it out in a summation notation. They would probably choose this formula for what they see here, And this is totally true, totally correct. It's just that the sum from 0 to infinity of number times ratio to the n, that form is the more standard way to write it. Theorems about geometric series will be stated in terms of that form, so we do want to get used to it, starting from 0 like that. So a few more examples. How about 1 minus half plus fourth minus an eighth plus 16th minus, and so on forever? I suggest n goes from 0 to infinity of this. Just see if it works. When I put in n as 0, I'm just going to get a 1 out. When I put in n is 1, I'm going to get that minus half. When I put in n as 2, I get minus half times minus half, which is a 4th, and so on. It's really working. And so in the standard form, I just stick a 1 there for my c, and my ratio term is minus half. The r is minus half. This is actually a geometric series, 10 minus 50 plus 250 minus 1250 plus something minus something forever. And in order for me to figure out how to write it in standard form, it might be a good idea to factor out a common factor of 10. So that 10 there is going to become my c. And then I look at the other terms and see if I can get some powers going on there, powers of something. And I realize I could do powers of 5. 1 is 5 to the 0, and then I've got a 5 there is 5 to 1. Now, when it comes to writing things down in standard form, I've got to come up with a ratio term so that I can account for the minus, plus, minus, and so on, the alternating signs that I see there. And it turns out minus 5 to the n is going to do it. Okay, so I've written that geometric series in a standard form. This time the c was a 10, and the ratio r was a minus 5. So thinking now ahead about whether a geometric series converges or not, and could we find what it converges to when it does converge? It's kind of a two-step process. We're first going to analyze the sequence of partial sums. Because after all, the limit of the sequence of partial sums is what the infinite series is. And then we'll figure out about infinite series. So we've got a theorem here that helps us deal with partial sums. It's called partial sums of a geometric series. And it says that the capital Nth partial sum turns out to be that simple little closed form expression as long as your ratio is not equal to 1. If it were equal to 1, then you'd be divided by 0 here. So how should we prove this? Well, I am just going to write down the capital Nth partial sum, and then I'm going to multiply both sides of that equation by r. So on the left, I'll get r times s capital N. On the right, I got to multiply each one of those terms by r, and so I'll just distribute the r through. And so instead of a c, I'm going to have a cr, but I'm going to write it underneath this cr. And instead of a cr, I'm going to have a cr squared, which I write underneath here. And I keep going like that. Like the cr to the capital N minus 1, when it's multiplied by r, it becomes cr to the capital N, and I'm just writing it under here. And then cr to the capital N gets multiplied by an r, and I just write it out at the end there. And then I'm going to subtract. I'm going to do s sub capital N minus r times s sub capital N. So that means doing this minus this. And there's a whole bunch of cancellation. The only stuff that's left is the c and the minus cr to the n plus 1. So now I know this fact. And I will proceed to solve for s sub capital N. And when I do, I have this expression. So you can see this makes sense as long as r is not 1. You know, as long as r is not 1, we can start with here. We can divide both sides by 1 minus r and get to here. Okay. Next up, theorem 3, sum of a geometric series. So this is where we ask, okay, can we figure out what the limit of the partial sums is? So let's see the non-zero, which you need for a geometric series. And suppose that your ratio term is less than 1 in absolute value. Suppose it's between minus 1 and 1. Then the geometric series actually converges, and it converges to this number. Let's prove that. Well, the geometric series is, by definition, the limit of the partial sums. But we have a formula for them. And that's because r is between minus 1 and 1, so it's not 1. So we can use theorem 2. And then we can just say, all right, let's take the limit of the top over the limit of the bottom. The limit of the bottom is just 1 minus r. The limit of the top will be this constant c times the limit of this difference, which is the limit of the 1 minus the limit of this other stuff. So we're down to thinking of what is the limit of r to the capital N plus 1 as capital N goes to infinity. Well, remember that we're assuming that the absolute value of r is less than 1. That is, we're assuming that r is between minus 1 and 1. And here we are raising a number between minus 1 and 1 to bigger and bigger powers. And so we're multiplying it together by itself a lot of times, and it gets smaller and smaller because it's less than 1, bigger than minus 1. So r to the capital N plus 1 goes to 0 as n goes to infinity. So that limit there just works out to c times 1 minus 0 over 1 minus r. It works out to be c over 1 minus r. We're done. Now, if the absolute value of r is bigger than or equal to 1, this infinite series, this geometric series, will diverge. And I'll just show you a couple of special, a couple of examples. Like, what if r is 1? Then you're really looking at just adding together a bunch of c's, because 1 to the n is always, 1. And when you add together a bunch of c's, you're either going to converge to infinity or to minus infinity if your c was a negative number. What about if r was negative 1? then r to the n alternates between 1 and -1, and so your partial sums, they will flip around between sometimes they'll be c and sometimes they'll be 0, and there won't be any chance to converge to just one number. So just keep this in your mind. Only when the absolute value of r is less than 1 does the geometric series converge. Of course, we're assuming all the way that c is not 0. If c is 0, then all of these terms would be 0 anyway, and the infinite series would just converge to 0. So we need to get a little practice of recognizing geometric series when we see them and figuring out what they converge to, if they converge at all. So how about this infinite series? Can we write it standardly as geometric series? I think we can. We write out its terms. We can factor out a fifth. And then we can look at the rest and see if we could express the rest as like a fixed number to powers. And we realize, oh, we can. This is a fifth to the 0. This is a fifth to the 1. This is a fifth to the 2, and so on. And so what we're really looking at is the sum, little n goes from 0 to infinity, of 1/5 times 1/5 to the n. Geometric series, ratio term less than 1 in absolute value, converging therefore to c over 1 minus r, 1/5 over 4/5, simplifies to 1/4 if you like. What could we find the sum of this infinite series? Well, it's not quite the standard form for a geometric series. It sure is close, though. It's got like a c and it's got an r to the n power. It's just that you're starting at 2 instead of 0. So I suggest that you just write this as the sum from 0 to infinity, but then take away the sum from 0 to 1. And then this geometric series, the ratio is 0.1 between -1 and 1, so it converges to the c over the 1 minus r, and then I just subtract off the 0 term and the 1 term from the sum. So I could simplify that if I wanted. Another approach to this kind of thing, instead of like subtracting off, is write out your terms and then just see if you can get it into standard form right away. Like what I might do here is I might factor out a 0.03 from each of those terms. That'll be my c. And then I'll have like a 1 here, and I'll have a 0.03 here, and I'll have a 0.003 here, and so on. And I'll have a 1 here, and I'll have a 0.01 here, and so on. And so then I'll see that I could use 0.1 to the n as my powers. So if you just write out the terms, then look for powers, you eventually come to this, and then you can see right away it converges to this. So this is actually the same number as this. Here's something that looks a lot like a geometric series. It does go in from 0 to infinity. It's just that you don't have like powers, 1 power of n. You've got 2 powers, and they aren't n's powers, like 3 to the 2n here and 10 to the n minus 3 here. So what's up with that? Can you write this as a geometric series? Yeah, because 3 to the 2n is 3 squared to the n. 10 to the n minus 3 is 10 to the n times 10 to the minus 3. I'm going to take that 10 to the minus 3. 1 over 10 to the minus 3 is 10 to the 3. So I've got myself a constant term of 4 times 10 to the 3. And then I've got the rest of this stuff. 3 squared is 9. And then I've got 3 squared to the n. I've got 10 to the n. So that's 3 squared over 10 to the n. I've got myself in standard form. I've got my constant, 4 times 10 cubed, and this bit here is a 0.9 to the n. So I'm in totally standard form. My ratio is between -1 and 1. So I go to C over 1 minus my ratio. That turns out to be 40,000 this time. How about sum n goes from 0 to infinity of 2 plus 3 to the n over 5 to the n? Well, that smells like a geometric series too, but it actually turns into two of them. If I take it and break up the fraction, I've got a sum of 2 over 5 to the n and a 3 to the n over 5 to the n. And I can look at the 2 over 5 to the n, and I can write it as 2 times 1/5 to the n. That looks like standard form. And here I could say that's 3/5 to the n, and then I could just stick a 1 to the outside to be my little constant term. And the next move here is a little shady. I've got these terms here, infinitely many of them added together. And what I'm saying is that I can move all the terms that look like this together and move all the terms like this together. Okay, so it's like doing commutativity with like infinitely many numbers being added up at once. That is a little shaky, but there's actually a math theorem that says that if this and this both converge, then that's okay, you can do that. So let's check. Does this converge? Does this converge? Oh yeah, they do. They're both geometric series, and the ratios are between -1 and 1. This one converges to this, and this one converges to this. So I could simplify that, but I have found that this infinite series does converge by breaking it up as the sum of two geometric series. One last little application of geometric series, just to show you a little bit about why they're just all over the place. Here's a probability problem for you. Say that you got two guys, Abe and Bo, and maybe they are, I don't know, they go to college in 19th century Europe, where rambunctious college males would often, they would get into fights with each other, and then they would resolve these fights by having a duel. Okay, so Abe and Bo need to have a duel, and they go out to a grassy field one early morning, and each of them has their little inaccurate 19th century pistols, okay? And they're standing about 20 paces apart, and they very honorably like take turns shooting at each other until somebody gets hit. And of course, these are very inaccurate and not very powerful guns. So like maybe nobody will die. Somebody will just get hit and they'll stop. So like, let's say that Abe, when he shoots, he has a 40% chance of hitting his target. And when Bo shoots, he gets a 60% chance of hitting his target. Bo's a little bit better shooter. So they decide to make things kind of even out. They say, let's have Abe go first. Okay. What would be the probability that Abe eventually wins this duel? You don't really win something like that, but what's the probability that he's the one who's left standing? So you can actually think about the event of Abe winning as being broken up into infinitely many possible ways for that event to happen. Abe could win on his first shot. Abe could also miss his first shot, and Bo misses his first shot, but Abe hits on his second shot. So he would win on his second shot. Or it could be that Abe misses, then Bo misses, then Abe misses, then Bo misses. Abe is up for the third time and he hits. That could happen. Then Abe would win on his third shot. And you could go on like that for infinitely many ways that Abe could eventually win. And if you add up the probabilities for all those ways, that's infinitely many little probabilities, then you would get the probability that Abe wins the duel. So we just need to find the probabilities of each of these ways and then see if they're an infinite series that we can sum. So what's the probability that Abe wins on his first shot? Well, that'll be 0.4 because he has a 40% chance of making a shot. What's the chance that Abe wins on his second shot? Well, for that to happen, you got to have Abe misses, Bo misses, then A hits. Shots are independent of each other. So what we could do is just multiply the probabilities for missing and hitting shots. 1 minus 0.4 would be the chance that Abe misses. 1 minus 0.6 is the chance that Bo misses. 0.4 is the chance that Abe hits. And then how about the chance, the probability for Abe to win on his third shot? Well, now you've got to have the four things, the four misses, okay, which have these chances. Chance of Abe missing, chance of Bo missing, chance of Abe missing again, chance of Bo missing again, and then we got to put on chance of Abe hitting on that third shot. And you would keep going like that forever. But what you definitely see is a pattern here. Every one of these terms has a 0.4 as a factor, okay? And every one of these terms has a power of 1 minus 4 times 1.6 times 1 minus 0.6. There's a first power here. There's a second power here. There's going to be a third power in the next one. Oh, and there was a 0th power here. So I could actually write that infinite series in standard form as a geometric series, like that. And 1 minus 0.4 is 0.6. 1 minus 0.6 is 0.4. 0.6 times 0.4 is 0.24. The ratio in this infinite series is 0.24. It's between minus 1 and 1. So this infinite series converges to the constant term over 1 minus the ratio. That actually reduces to 40 divided by 76, which is a little bit more than 0.5. You know what? Abe has a better than 50% chance to prevail in this duel, even though he's a weaker shooter, and that's because he gets to go first. That kind of more than balances out his disadvantage as a poor shooter. So very interesting application. Like I said, geometric series are all around. This is far from the last time we'll see them. See you later.